Hi, I'd like to begin by thanking the Permutation Pattern Committee for the opportunity to tell you about algorithmic solutions to problems in permutation patterns. This is presented by me, Henning Úlfarsson, but is joint work with many other people, including Michael Albert, Christian Bean, Anders Classen, Emil Nadau, and Jay Pantone, as well as numerous students which I'll mention below. Now, a while ago, Knuth asked which permutations are sorted by a single pass through a stack. Just to remind you, a stack is a device that takes a permutation as input, for example 3, 5, 2, 4, 1, and tries to return it sorted, in this case 1, 2, 3, 4, 5. It operates under certain sets of rules. For example, we'll start by putting 3 down on the stack. We don't want to put 5 on top because then 5 will leave the stack and be too early in the output. It'll be before the 3, which is not a good idea if you're returning or attempting to return 1, 2, 3, 4, 5. So let's back up a bit and let's output 3 from the stack, put the 5 down on the bottom. It's fine to put 2 on top of 5, and in general we try to keep the stack in increasing order, read from top to bottom. We don't want to put 4 on top of 2, so we output 2. Put 4 on top of 5, put 1 on top of 4, and now the input is exhausted, so we just empty the stack and have our output, which is clearly not sorted, and so the stack failed. And Knuth wanted to know why it fails, which permutations are sorted and which are not sorted by a single pass through the stack. And now, to get permutation patterns into the picture, let's realize that not sorted means the output contains the pattern 2, 1, which we can draw like this. And if the output contains 2, 1, the same 2 elements making up an occurrence of this pattern 2, 1 must have also been an occurrence of 2, 1 in the input. And furthermore, there was something that caused the stack to fail to sort these 2 particular elements correctly. What should have happened, if we mark these points with an X and an O, is X goes into the stack, some stuff happens, there could be intermediate elements between these 2 elements in the entire input permutation. Then the small element O should have landed on top and then left the stack prior to X leaving the stack. But this didn't happen. And the only reason why this can't happen is the presence of a third element that's bigger than the X, which will cause X to leave the stack before O has a chance of entering the stack. And so the input doesn't just contain this 2, 1, it contains a bigger element between them. In other words, the input contained something that looks like this, or the permutation pattern 2, 3, 1. And so we've answered Knuth's question. A permutation is sorted by the stack if and only if it avoids 2, 3, 1. And the simple observations we were making are enough to answer a much broader question. If the pattern P is in the output, then the input contains a pattern P prime satisfying several conditions. It has the same length as the pattern in the output. And if there is an inversion in P, some big element j before a small element I, then it's also an inversion in P prime, and there must be a, let's call it k, bigger element between them to make sure that this particular inversion stays an inversion in the output. This is exactly the same case we were looking at previously. We also need to say something about non-inversions. So if you have a non-inversion in the pattern P in the output, then either the same is true in P prime and nothing much else needs to be said, or it's an inversion in P prime with no k, which means it's an inversion that gets fixed by the stack. If this is in the input, it must stay and it needs to get fixed into a non-inversion in the output, which means there can't be an element popping j off the stack before I enters the stack. And here we see our favorite, the mesh pattern entering the picture. And so let's look at another classic question. Let's try to describe the permutations which avoid 2, 3, 1 after sorting. If we know the answer to this question, we have described the so-called West 2-stack sortable permutations, which are the ones that are sorted after 2 passes through the stack. And so if we're worried about a 2, 3, 1 in the output, what that might have looked like in the input is either a 2, 3, 1 or a 3, 2, 1. This is because non-inversions in the input stay as non-inversions, but inversions in the input can become non-inversions in the output. So these are the only 2 candidates for the input to get a 2, 3, 1 in the output. If we take a look at what we were doing above, we need to make sure that this inversion stays as an inversion. So there needs to be a big element between them, but that's fine, it's already there. This inversion needs to stay an inversion. So we need a big element making sure that happens. So that has to be in this box, which will take care of the other box as well, if we didn't notice that we already have that point playing that role. And so we have come upon this pattern 2, 3, 4, 1. Looking at the second candidate 3, 2, 1, we need to make sure that these 2 elements stay as an inversion. So we need a point in this box. We also need these two elements to stay as an inversion. So we need a point in this box. But we need these 2 points making an inversion in the input to become a non-inversion in the output, which means there can't be anything here. And so the only way to satisfy all of these conditions is to have nothing here and a point here. If we scale this up to a full permutation pattern, we get 3, 2, 4, 1. This 4 here splits the shading on its left. So you could draw it like that. You can actually skip drawing this. You can either see that directly in the special case, or you can use algorithmic tools, which we'll talk about later, to answer that question for you. So what we have here is now, we've described the pre-image of the permutation class AB231 as the avoiders of a single classical pattern and a single mesh pattern. This can actually be done for any permutation class. As I showed with Anders Claassen. And the same description can also be generalized for some avoiders of mesh patterns. This was the topic of Hjalti Magnussen's MSc thesis, where he also considered other sorting operators, such as Q-sort and other natural operators. But it would be nicer to having to think less and just get these descriptions of sets we're looking at, like this pre-image, in terms of patterns, without having to go through hoops to get this description. And there's an algorithm to do that called the BISC algorithm, which I'll show you now. Programming, and we'll use Python and the Permuta library to do it. You can get Permuta from GitHub or just doing pip install Permuta. If you run into any issues, you can ask us for support on our Discord server and we'd be happy to help you. So let's fire up Python and Permuta. I'll be using PyPy, but you can just as well use plain Python. And I'll do from Permuta import star to import everything I need. I can now define and work with permutations. We're programming, so things will be zero based. And let's draw this permutation. There's a function that can give us the ASCII plot to do that. And we want to use the BISC piece of Permuta. So let's import functions related to BISC. And let's bring back our old friend, the stack sortable permutations. So I'm importing from a collection of permutation properties, importing the stack sortable function. So I can do things like check if the permutation I defined above is stack sortable or not. And now the easiest way to use BISC is to use a function called autoBISC and just give it the property we imported. And this will generate some permutations and try to figure out which pattern should be avoided to satisfy the property. And just to see some more impressive output, let's take a look at the second set we investigated earlier, the West 2 stack sortable permutations. In other words, the permutations that are sortable by 2 passes through the stack. So we'll do AutoBisc again, and now we'll look at the property of being West 2 stack sortable. And now let's take a look at what it's doing in slightly more detail. It will start by trying to learn patterns of just length 2 using permutations of length 4. It quickly realizes you need to search for longer patterns. It tries to display the output, but there isn't any output yet. It now tries to learn length 3 patterns using permutations of length 5, realizes it needs to keep going into higher lengths. And finally, when it's looking for length 4 patterns using permutations of length 6, we start to get something. Here are the patterns that were found. We can see they're exactly the same as we found by hand. And then it starts doing some sanity check. Since it was using permutations of length 6 to learn, it will sanity check 2 lengths higher. And when it's satisfied with that, it will try to use fewer patterns to describe the property of being West 2 stack sortable if it's possible. Here we need exactly these 2 patterns, and so this is the basis that Bisq will guess and sanity check again. And here is just a different representation of the output, which is easier to copy and store if you need for later. So what's happening here is we're using the West 2 stack sortable permutations to guess, so strong emphasis on guess, the patterns you need to avoid to satisfy that property. Now once you have the guess in hand, it's often easy to prove that the guess is true. So this is not a theorem prover, it's a conjecturer. Okay, let's see it fail. So I'm not going to take the so-called West 3 stack sortable permutations. Let's just clear the screen. So we import the property of being West 3 stack sortable, and we try to run AutoBisc on that. It will find some patterns, but realize it's not sufficient. It will start generating permutations of length 9 satisfying the property and trying to learn from them. It will find some more patterns. That's still not enough. It will add permutations of length 10 and so on and so forth, because there seems to be no finite basis of mesh patterns that describes this property. I want to highlight some successes though, so let's stop it and clear the screen. I want to import something called BKV sortable from a recent paper by Anders Classen and co-authors. And there are some theorems in there that we can define the property for. I run AutoBisc on that. To recreate the statement in the theorem. Here we see pretty big basis of mesh patterns that guessed at first. But then in the later stages of the algorithm, it will keep going and try to find a smaller basis. Now seems to be happy. So it's found the basis with 3 classical patterns with length 4 and a single mesh pattern. So if you're looking at a specific set of permutations, wondering whether they're described by mesh patterns, this might be a good place to start to help you conjecture a description. Now that we've seen a demo of Bisq, it's maybe time to tell you where the name comes from. BI comes from Billy, from Sarah Billy, who wondered if it could be possible to learn mesh patterns. S is for Steingrimsson, as in Einar Steingrimsson, who was my postdoc advisor and introduced me to the area of permutation patterns. And Anders Classen is the C, because he helped me a lot in the initial stages of thinking about how this algorithm could be implemented. Now, the Bisq algorithm sometimes has redundancy in the outputted patterns. And I'll simplify the issue slightly by imagining how silly it would be if the output of Bisq would be something like this. And I say this is silly because we're saying you're looking at permutations that avoid having an inversion and also avoids having a descent. One of these patterns is enough to describe what we're looking at. We're just looking at the increasing permutations, or the identity permutations if you prefer. Now clearly, if pi contains a descent, it contains an inversion. If pi contains this mesh pattern, it also contains this classical pattern. For the other direction, the permutation contains this classical pattern. Let's try to systematically prove it also contains the mesh pattern. So we'll start with an occurrence of 2, 1 in a permutation. And we'll not just start with any old occurrence. We'll start with something we tend to call a forced occurrence. Forced in the sense that out of all the occurrences of 2, 1, this particular occurrence we're looking at will have this point as far left as possible and this point as far right as possible. We first choose by pushing this point as far left as possible and then pushing this one as far right as possible. Okay, and then there are 2 cases to think about. When you're looking at this occurrence, either it just so happens there are no points up here, or there's at least one point somewhere in this region of the permutation. Now this would be weird because you now have another occurrence of 2, 1. You're still using the same point for 1 as in the original occurrence, but the point playing the role of 2 is now further to the right, violating this force condition here. So this can't happen. It means the branch here we're looking at is, you could say it's a contradiction, or there are no permutations that live on this branch. And so everything happens in this case. And again, we can split into 2 cases, depending on whether this region is empty or contains a point. Well, now we have another occurrence of 2, 1. this one, which also violates the force condition. Now, this point is further to the left than should be possible. So this branch can be discarded. We just need to focus here. And as you can guess, finally, either this box is empty or contains a point. And by exactly the same kind of argument, you'll realize that this can't happen and everything lives here. So if a permutation contains a 2-1, it also contains this mesh pattern version of 2-1. And these simple steps I was taking, these were generalized into what we ended up calling the shading algorithm, which Thomas Magnusson described and implemented in his master's thesis. Murray Tannock then considered a different type of this problem where you're looking at mesh patterns inside permutations that avoid some other classical patterns. Now, this shading algorithm, it's powerful enough to classify all mesh patterns of length 3, so tell you which ones imply the other, except for a single pair of mesh patterns which we had to do by hand. And I can tell you more about them sometime in the future, but it was both amusing and annoying that the algorithm could do everything in length 3 for us except a single special case. Now, when we were working on the shading algorithm, we thought a lot about pictures of this form, and we had to do some special casing, such as thinking about what if this region is just increasing and maybe this one is just decreasing, or if this piece here avoids 3-2-1, or if this piece is increasing, there might be nothing here, maybe this avoids 2-3-1. And so we were always thinking about these things and what kind of permutations could be drawn on them. We also wanted to know the enumeration, how many permutations can be drawn on a picture like this. And this led to the creation of the so-called struct algorithm, which tried to express permutation classes as disjoint unions of permutations which can be drawn on such pictures. And Bjarki Guðmundsson and Bjarni Kristinsson wrote master's theses about these. We then ended up generalizing the struct algorithm to the telescope algorithm. And there have been numerous master students contributing to that work: Ragnar Árdal, Arnar Arnarsson, Unnar Erlendsson, and Thomas Magnusson. And so what we try to do here is systematically describe classes by breaking them up into easier cases until we have something that technically is a combinatorial specification, but we often call them proof trees as well. So let's go back to the answer to Knuth's question. Let's look at permutations that avoid 2-3-1. And so here we have the set of permutations avoiding 2-3-1. This is an infinite set. We can separate a piece of it, a very, very finite piece, the permutations that avoid having a point. We denote that with a red point. You avoid having a point. So here there's not much going on. the only permutation that lives here is the empty permutation. On the right hand side we have the rest. They have at least 1 point, and so we use blue to denote that. You're still of course avoiding 2, 3, 1. Now you've all seen this argument a million times. Let's place the topmost point of the permutation. Of course you still need to avoid 2, 3, 1 on both sides. You still need to be careful. You don't want to get a crossing 2, 3, 1 in this way or in this way. And you also don't want to get a 2, 3, 1 that uses the placed maximum, which would look like this. And now we see that these long 2, 3, 1s crossing the boundary are redundant information, because we really just have to be careful not to have a 2, 1 crossing the boundary. So we need to avoid having a 2, 1 across the boundary, and we have to avoid having 2, 3, 1 on either side. What this 2, 1 here really says is the points on the left have to be below all the points on the right. And that leads us to this picture, which you've of course seen multiple times before. We now have 3 independent pieces in this picture, the point, as well as 2 smaller 2, 3, 1 avoiders. And now, like we usually do, let's throw some generating functions into the picture. This is f. There's a single permutation here of length 0, so that's a 1. Let's call this g. And after this gymnastics with g, we ended up factoring g into a point, x, and 2 copies of the root of the tree. And let's solve this. So f is 1 plus g, because we took a disjoint union here at the start. G factored as x times f times f. Let's put that together. We have 1 plus xf squared, which we can write in the usual form of a quadratic equation, 1 minus f plus xf squared. If we solve this, we get 1 plus minus root of 1 minus 4x over 2x. And then looking at the initial conditions, we can see that the minus solution is the correct solution. Okay, and the telescope algorithm was developed to automate all of the steps that I just did, as well as doing several other steps. And we'll now see a demo of the telescope algorithm. A different library, which you can get from GitHub as well, or you can get it directly by installing with pip. And again, if you run into issues, please talk to us on Discord. So I'm going to move back over to the terminal. I'm going to clear my screen, import everything I need from tilings. I'm going to import the telescope functionality. And the telescope has many different ways of working with permutation classes. And we've organized these many different ways into things we call strategy packs. Because if we try to use all the methods at once, things kind of explode. So you want to narrow down the options into strategy packs. What we were doing by hand previously was basically just doing point placements. We placed a maximum point, and that seems to be enough to understand the 231 avoiders. So let's keep things simple and use the point placements strategy pack. And I'll initialize a telescope with the avoiders of 231 and the pack we just created. I'll then try to run an auto search and store the output in this spec variable. Spec here stands for specification, because if we are successful, the output will be a combinatorial specification. And lo and behold, we are successful, and we get this nice textual description of what's happening. It's really the exact same thing as we did. We started with the root of 231 avoiders. Again, everything is zero-based in programming land. You either have just the empty permutation, or you have at least one point. Here we just state the bold claim that we understand the empty permutation. If you have at least one point, let's place the maximum. We realize that then the left and the right split vertically like this. And then this part of the picture can be factored, just like we did by hand. And this isn't then enough to understand the avoiders. And here we also say we understand the single point. Now, remember we saved the output in a variable called spec. This can now be used to count the 231 avoiders. You can quickly get up to length 100 and even beyond if we want. We can randomly sample. So let's pick a random permutation of length 25, store it in the variable GP. GP stands for gridded permutation. And let's see what we got. That's the random 231 avoider we chose. And now to make things a bit more interesting, let's look at the 1, 2, 3 avoiders. I will need to change the pack. I'll use something called row and column placements, actually just restricted to rows. And I'll use the so-called fusion strategy, because that's apparently what you need for 1, 2, 3 avoiders. I'll initialize a telescope like before on the 1, 2, 3 avoiders with this new pack, and I'll search for a specification. Again, we find it. It's a bit more complicated than the one we had previously. One thing that makes it complicated is to understand 1, 2, 3 avoiders, you need to understand these mergings of decreasing runs into a single decreasing run. With this in hand, we can enumerate again. But before we do that, I want to go to a slightly more ambitious class. Let's move up to the 1, 2, 3, 4 avoiders. And let's run auto search on that. And note that I'm using the same pack that I used for 1, 2, 3 avoiders. And so now we're trying to get the 1, 2, 3, 4 avoiders. Of course, this is going to take more time. The 1, 2, 3, 4 avoiders are much more complicated than the 1, 2, 3 avoiders. And we'll need to be slightly patient. It only takes a few hours, but we can use the time for some meditation, thinking about our place in the world. Oh, finished a few hours earlier than I expected. So here it is. Again, it's a bit too much for a human, but we should keep in mind that each individual step is actually very simple. Here, for example, we're just factoring out a single point. And now this pretty large specification can be used, for example, to count the permutations avoiding 1, 2, 3, 4. Let's go up to length 15. Have to wait a bit because it's a more complicated set than the ones we were looking at previously. Now that we've seen a quick demo of the telescope algorithm, I want to mention that Christian Bean is also delivering a poster describing the algorithm in a bit more detail. But please head over to GitHub and read more about the algorithm, try it out, or ask us for help on the Discord server that is linked from the README on GitHub. As we saw in the demo, we needed a, let's say, fancy strategy. And if I had spent time on the details, I would have needed two variables to enumerate AV123. One of these variables is often called the catalytic variable, whereas the first variable is just accounting for the number of points in the permutation you're looking for. As with much of the problems in life, we can use mesh patterns to solve them. Well, at least we can use mesh patterns to get rid of the extra variable we had to use in enumerating AV123. So what we do here is we take our set, AV123, and split it into a disjoint union. First half will have 0 left to right maxima, and the other will have more left to right maxima. Of course, there's not much going on here, there's just the empty permutation. On this side, there's a lot more perms. So let's focus our attention on the second half of the disjoint union and actually split that into its own disjoint union. Here we have at least one left to right minimum, so let's draw a few of them. I'm going to take a disjoint union based on whether there is nothing in these diagonal cells if you were to draw the full grid of the permutation. So on this side, there's at least 1 point in one of these diagonal cells. And this is where mesh patterns enter the picture, because what does this point look like? Well, it itself is not a left to right minimum. It has to see a left to right minimum to its southwest. This is a left to right minimum, so there's nothing below it. And the fact that our point is in a diagonal cell means that there's nothing here or here. Over here it means empty and empty. Furthermore, there might be many points in this diagonal cell, But to point to a particular point, I can say I'm going to take the point that's closest to the left-right minimum. Say the bottommost point or something. So this box is also empty. And that's the mesh pattern we're going to use. On the other side of the disjoint union, where there are no such points, there's a trick one can do. And here's the trick. I'm going to do it with the case of 3 left-right minima. We want to realize that that case is just like the case of 2 left-right minima. We're avoiding 1, 2, 3, so what's happening inside these boxes is we don't want to have a 1, 2 here. We don't want to have a 1, 2 here. And we don't want to have a 1, 2 here. We don't want a crossing 1, 2 like this, and we don't want a crossing 1, 2 like this. This is exactly the same thing that happens if you just have 2 left-right minima. So we can take the bigger picture and kind of just factor out a single point and be left with the smaller case of 2 left-right minima. If we want to be slightly more precise, there is some shifting going on. This left-right minimum shifts to here, and this one shifts to here, and this one gets popped off. If you want to get a bit fancy, what's happening here is you can take the complement of where we started, here with 3 left-right minima, bubble sort. This will cause exactly the shifting we want in the left-right minima. We remove the maximum, which is now sitting at the back of the permutation, and then we take a complement again. This will do exactly what is shown here in the picture above. Okay, so now I want to use these tricks to get a nicer description of the 1, 2, 3 avoiders. Here's the pattern, L, I'm calling it, we have to use. And here's a picture we need to complete for the 1, 2, 3 avoiders. Again, we can say either I have no points or I have a single point, denoted here in blue at least. We're still avoiding 1, 2, 3. And let's first take care of what's happening here. If we were to place the minimum point in the permutation, we would still have to avoid 1, 2, 3 here. We have to avoid 1, 2 here because we have the minimum there to the left of us. And we also have to avoid a 1, 2, 3 crossing like that. Okay. Then we're taking a disjoint union, depending on whether we contain L, this magic mesh pattern, or avoid it. Okay, let's start here on the right, in the case where we are avoiding L but have at least 1 point. Let's place the leftmost point. Now we have to avoid a 1, 2 up here, a 1, 2, 3 down here, a crossing 1, 2, 3. We have to avoid L, the mesh pattern, here. Might have to avoid it here, but actually no, because of this shading here, L could not exist in the upper box over here, because shading means empty, and there's always a point that lands in the region that's supposed to be empty. So we can actually forget about avoiding L up there. However, the entire picture has to avoid L, which means we have to avoid this smaller mesh pattern I'm drawing, because if this smaller mesh pattern appeared, it, along with the leftmost point, would exactly create L, which we don't want. Okay, let's move over to the left-hand branch. Here we contain L, which means there is an occurrence of L. I've drawn that here. Because we're avoiding 1, 2, 3, this box has to be empty. This box has to avoid 1, 2, 3. This has to avoid 1, 2. Have to avoid 1, 2, 3 crossing like this. I don't want a 1, 2, 3 here. I also don't want a crossing 1, 2, 3. I don't want a 1, 2 over here. And now we have to be careful. I'm placing an occurrence of L, but for uniqueness, I need it to be a special occurrence of L. This is just a more complicated version of placing a single point like this. When you place it, you have to be careful with uniqueness. So we do things like placing the bottommost point. It can be only one bottommost point. We also place the leftmost point. It can be only one leftmost point. So we have to do something similar. We have to take a forced occurrence of L, and I'm going to take the bottommost occurrence of L I could find in a permutation. This implies there can't be an occurrence of L further down in the permutation, so I have to avoid L down there. I also have to avoid the same length 1 mesh pattern that I drew over there on the right, because if this happened, these 2 points would give me an occurrence of L further down. But that's not supposed to be able to happen, because these 2 particular points are supposed to be the occurrence of L that's as far down as possible in the permutation. Okay, and now you kind of have to believe me that I've shown you all the information you need to see in this picture. Okay. We can factor, because there are now a lot of independent pieces in this big picture. There's a point, which we can factor out here. There's the piece up here, and there's another point, and then there's the piece over here. On the right side, we can also apply the trick I did previously. This bubble sort nonsense. If you contain at least one point, avoid L, which means there are no points in the diagonal cells, then we can factor out a single point and then have a quote-unquote normal permutation left over. Just like we did here, factor out the point and we have a normal permutation left over. Okay, now if we add some colors, I claim we're done. So here is a piece I'm going to make purple, which is really the same thing as over here. The point is just in a different place. And these two are the same as what we have over here. Again, the point is has just been factored out on the left. And now we can throw some variables in here. Let's call this an f. 1 for the empty permutation. Let's call this g. Let's call this h. This will be I. The purple thing is a G. The green thing is an I. The point is X. And then we have the root F again. Stare at this for a second and write down the equations. So we have, try to fit this better, let's see. We have F is 1 plus G, disjoint union at the root. G is also a disjoint union into H and I. H factors, that's a product, into G times I. And then we have I is X times F. If we start by taking the last two equations together, we have H as X times F times G. Then G is XFG plus XF. Solve for G, and you have XF over 1 minus XF. Combine that with the first equation. You have 1 plus XF over 1 minus XF. Solve for F. And you'll have 1 minus the root of 1 minus 4x over 2x. Of course, you would get two solutions first, but then you would pay attention to the initial conditions, and you would choose the minus as the correct solution. And there we have our old friend, the generating function of the Catalan numbers. Now, that was nice. No catalytic variables, just mesh patterns. The foundations of the algorithm are strong already. It can already enumerate every AVB, where B is a basis of patterns of length 4, except for a handful of cases, such as, of course, 1, 3, 2, 4. The mesh pattern strategy I was showing above has not been implemented yet. We're also adding features such as things we call forests, where we drop the condition of returning a combinatorial specification, but rather output, let's say, a set of equations that can still be solved to give the enumeration of the inputted AVB. Furthermore, we also plan on automating finding bijections between permutation classes by first finding a specification for one of the classes and then using that as a guided search for a specification for the other class, and trying to find an isomorphic specification. And they can be then used to map permutations in one specification to permutations in the other. And finally, we have also started to add the ability to enumerate classes with respect to a statistic, such as how many inversions there are in a permutation. But that's something you will hopefully hear more about at the next installment of permutation patterns. Thank you very much.